Now that we understand orthopara directors, let's take a look at an example of a meta director. And so we start with nitrobenzene. And if our goal is to nitrate nitrobenzene, all right, we need to add something like fuming nitric acid, sulfuric acid as our catalyst, and we also need to heat it up. So we need to force this reaction to occur because nitrobenzene turns out to be not as reactive as benzene itself. And so the end result is to add a nitro group onto the meta position, right? So we added a nitro group onto the meta position on our benzene ring. And so the meta product dominates here, not the ortho para. Let's see if we can figure out why by looking at some resonance structures for this mechanism. And so we'll start with an ortho attack, right? So in our first example here, we'll do an ortho attack where we add the nitro group onto the ortho position. So remember, the function of the nitric acid and sulfuric acid is to generate your electrophile, which is the nitronium ion right here with a +1 formal charge on the nitrogen. And so that's our electrophile. The benzene ring is going to function as the nucleophile, and so these pi electrons here are going to attack this nitrogen, pushing these electrons off onto the oxygen. So let's go ahead and look at the results of our nucleophilic attack. Right, we have a nitro group right here. I want to show an ortho attack, so I'm going to show the NO2 adding on to the ortho position. So here's the ortho position with an NO2. That carbon also has a hydrogen bonded to it. Let's go ahead and highlight some electrons, right? So these pi electrons right here are forming a bond between the nitrogen and the carbon on our ring. So that takes a bond away from this carbon, and so that's where our +1 formal charge is going to go. And then, of course, we still have these pi electrons in our ring like that. Let's go ahead and draw a resonance structure for this ion here. So we have a pi bond next to a positive charge, right? So we could take these pi electrons and move them over to here. And let's go ahead and draw that resonance structure. So we have our ring, top nitro group. Right, over here we have the other nitro group in the ortho position. Right, we have these pi electrons at the top. We have these pi electrons over here now. So let's highlight those. So the pi electrons in blue have moved over to here, taking a bond away from this carbon. So that carbon gets a +1 formal charge like that. So there's a resonance structure. Let's go ahead and draw one more. So I could show, once again, these pi electrons moving down to here, and we have our ring. Right? We have this top nitro group, which I'm actually going to go ahead and draw in the formal charges, and you'll see why in a second. So this oxygen is a -1 formal charge, and this nitrogen has a +1 formal charge like that. So over here we have our other nitro group in the ortho position. Right? We have pi electrons here, and we just moved some pi electrons over to this position. So let's go ahead and highlight those too. So over here in red, these pi electrons have moved over to here, taking a bond away from this top carbon here. So that's where our +1 charge goes now. So we have a +1 formal charge on this top carbon here. And this is a destabilizing resonance structure. And we know that because we have a +1 formal charge in this nitrogen and a +1 formal charge on this carbon on our ring. And so like charges repel and therefore destabilize this resonance structure. All right, so we have a destabilizing resonance structure. And remember, it's actually really a hybrid of our resonance structures for our sigma complex. But one of those resonance structures is destabilizing, which means that this sigma complex is not very likely to form. So let's go ahead and look at a meta attack, and you'll see that we will not have a destabilizing resonance structure when we do a meta attack. So let's go ahead and once again show our nitrobenzene and our nitronium ion, and this time we will do a meta attack. So if I want to show a nitro group adding on to the meta position, I would once again use these pi electrons. So nucleophilic attack, right, pushes these electrons off, and so we're going to once again show the resulting carbocation here. So we have a nitro group right here. And this time we're showing the nitro group adding on meta, right? And once again, there's a hydrogen attached to our ring. And these pi electrons here, right, are forming the bond between this carbon and our nitrogen, taking a bond away from this carbon, so that carbon gets a +1 formal charge, and we still have, of course, pi electrons in our ring. And so that's our first resonance structure, right? We can draw another one. I could take these pi electrons and move them over to here. So let's go ahead and show the next resonance structure with our ring, our nitro group here, right? Our nitro group in the meta position, right? And hydrogen also attached to that carbon. Pi electrons here, and pi electrons have moved over to here. So let me highlight those. So these pi electrons have moved over to here, taking a bond away from this carbon. So we get a +1 formal charge here. Right? We can draw another resonance structure, taking these pi electrons, moving them over to here. And so let's go ahead and do that. We have our ring once again. Right, we have a nitro group in the top carbon. We have a nitro group in the meta position. Once again, we have hydrogen. We have these pi electrons, and we now have moved the pi electrons over to here. So let me highlight those. So in red, these pi electrons have moved over to this position, taking a bond away from this carbon. So we get a +1 formal charge on that carbon. And so these are the three resonance structures that you for a meta attack. And notice we don't have a destabilizing one, right? So in our three resonance structures, none of them have the two positive charges right next to each other, as we saw in the previous example. So it's not so much that the sigma complex for a meta attack is extra stable, it's just that the sigma complex for a meta attack doesn't have any destabilizing like charges repelling each other. And so because there is no destabilization, the meta sigma complex becomes the most stable one and the one that's most likely to form in your mechanism. And so that's why a nitro group on your ring is going to function as a meta director. Let's go ahead and do a para attack so that you can see that a para attack is going to give you the same situation as an ortho attack. So if I wanted to add the nitro group onto the para position, I would have to use these pi electrons over here this time. So nucleophilic attack. So the nucleophile attacks the electrophile, once again pushing those electrons off. And so we have our nitro group here, right? We have these pi electrons. We are now going to show the nitro group in the para position. So if I'm saying these electrons in magenta are going to form a bond with this nitrogen right here, taking a bond away from that carbon, so that gets our +1 formal charge right here. So a resonance structure would be to take these pi electrons and move them over to here. So let's go ahead and show the next one. So we have our ring. This time I'm going to draw out the formal charges on my nitro group, right? So I have an oxygen that's negatively charged. This nitrogen has a +1 formal charge on it. And my pi electrons, right? I have pi electrons here. I have my nitro group once again in the para position. And I have some pi electrons over here as well. So let's highlight those. So the pi electrons in blue, right, have moved over to here, taking a bond away from this top carbon, and so I can go ahead and draw a +1 formal charge on this top carbon. And once again, this is our destabilizing resonance structure. I have a positively charged carbon on my ring right next to my positively charged nitrogen. So like charges repel, this is the destabilizing resonance structure, which of course destabilizes the sigma complex for a para attack. Just to be complete, I can draw another resonance structure, right? So I could take these pi electrons over to here. So let's go ahead and draw our third one, right? So I have my nitro group, right? I have pi electrons here, and I have a nitro in the para position. And let me go ahead and highlight those electrons one last time. So I have these electrons in red, have moved over to here, taking a bond away from this carbon, and so that will get our +1 formal charge for our last resonance structure. So once again, remember that the sigma complex is a hybrid of these resonance structures, but since we can draw a destabilizing resonance structure, this sigma complex is not the one that's most likely to form. So the meta attack is preferred. So one more quick thing about meta directors. So an easy way to recognize a meta director. So we've seen in this example, our substituent has an atom that has a positive charge right next to our benzene ring. And so one way to look for a meta director would be, here's just a generic substituent Y directly bonded to our benzene ring. So the atom directly bonded to your benzene ring, if there's a +1 formal charge on it, we've just seen that resonance structures are destabilized for an ortho-para attack. Therefore, a meta attack is preferred. So you could look for a +1 formal charge, or you could look for a partial positive. And so that's just my really fast and easy way of figuring out a meta director. So in the next video, we'll look at much more detail about some other meta directors.